let's talk about the chain rule. In particular in this video, I want to talk about the chain rule for functions on two variables. But I want to start just by reviewing the chain rule from Calc 1. If f is differentiable at g of t, and g is in turn differentiable at t, then the derivative of the composite function f of g of t with respect to t is f prime of g of t times g prime of t. Now another way to think about that is that this composite function's derivative is the product of the derivative of f with respect to g, because that's what this collection of symbols is telling me. I'm taking the derivative of f, treating g like it's a variable, just leaving it alone in there, times the derivative of g with respect to t. And I can actually follow that through what we call a dependency diagram. I plug t into a function called g, and I get a g of t. And then I plug that g into a function called f, and I get a y value. And if I just look, I have one independent variable, I have one intermediate variable, so not really what I want to talk about in this video. I want to have two things in the middle, functions on two variables. And then I have the final thing, right? Plug t into g, plug g into f. All right, well, if I think about it, below f, I have one variable, one intermediate variable, so I could take the derivative of f with respect to g. Below g, I have one independent variable. I could take the derivative of g with respect to t. And then this is their product is telling me how to build a chain rule, right? This dependency diagram says take this and multiply it by that. Now, just to help us later on, let's think about f being differentiable at a variable x. And x in turn is a function on t, and it's differentiable on that variable t. So my dependency diagram would now look like this. T gets plugged into a function that gives me an x value. That x value gets plugged into a function that gives me a y value. I take a derivative with respect to x, one variable in the row right below the f, and then I take a derivative of x with respect to t. So the derivative of f with respect to the lone independent variable t is the product of df dx and dx dt. And there's my chain rule. Okay, so let's see what happens when we go up to functions on two variables. So here we're going to have the chain rule for one independent variable t and two intermediate variables. So I have a function that takes in an x and a y. But my functions, the points x and y come from functions, x of t and y of t. F of xy is differentiable at x comma y. X and y are in turn differentiable at t. So if we want to think about a dependency diagram, the lone independent variable t gets plugged into functions and get turned into x's and y's. The x's and y's get plugged into a function and in turn get plugged into f to form a z. Okay, a little bit different situation, but I still have one independent variable. I use that to calculate x and y. I plug those into a function called f to get a z. If I look at f, in the row of variables right below it, there are two of them. So I don't have a derivative there. I have partial derivatives. I could write the partial of f with respect to x. And then I could take the partial of f with respect to y. In the row right below the x, there's only the lone independent variable. So I could take the derivative of x with respect to t, and the same thing for y. And this is what I claim my chain rule will be. I can go down either side of my dependency diagram. Here, I would have a partial of f with respect to x times dx dt plus a partial with respect to y times dy dt. And that's my chain rule for a function on two variables where the two variables are a function of a lone independent variable. So let's do an example and see if I can convince you of that. There is a great explanation of why this is true that's in an appendix in your textbook, but we'll actually talk about the reason this is true after we've studied tangent planes, because that'll give us a way of thinking of studying what's called a differential, which compares to what differentials were in Calc 1, and we'll be able to come back to this idea and really thoroughly understand why it's true. But for now, let's do an example. So I want to give a function f of xy. So let's just let f of x comma y be x squared minus y squared. And I'm picking that because that's a hyperbolic paraboloid, right? Z equals x squared minus y squared. It's one of my quadric surfaces. And so I could actually imagine the origin as being this point right here. A z-axis coming, if I hold it like this, straight up out the camera, the x-axis and the y-axis. And the functions I'm going to use for x and y are going to be very familiar. X of t is cosine, and y of t is sine. And I hope when you see those two things written down as x and y, your brain's going, I know what those are, but I'm not going to say a word about them and what they are right now. Pause the video and see if you can figure it out. But I just want to use the chain rule to find df dt. And then I want to do a more common sense thing to find df dt. All right, so the chain rule says I should find the partial of f with respect to x. You know, nothing too challenging there. Let's just put this here. Partial of f with respect to x. So I take a derivative treating y like it's a constant. I get 2x. And I also need to take the partial of f with respect to y. And again, nothing too challenging. I get minus 2y. Now, I'm supposed to find the derivative of x and y with respect to t. Okay, so dx dt is equal to minus sine, and dy dt is equal to cosine t. So now, I should be able to write down df dt just using the chain rule. df dt is supposed to be the partial of f with respect to x, 2x, and that's ridiculously spaced, so I hope I did that for a reason, times the derivative of x with respect to t, so times minus sine t, plus the derivative of, the partial of f with respect to y, so it's going to be a minus 2y, go on, change that plus to a minus, and again, I'm going to leave myself some room because I'm going to fill something in there, times dy dt, cosine t. Okay, well, here's the big reveal. That said y, but I know what y is. Y is sine t. This says x, but I know what x is. X is cosine t. Because the whole point here should be to get a formula that's in terms of the lone independent variable t. This is the derivative of f with respect to the variable t. And so let's just look through this. What I have written there, df dt is equal to minus 2 sine t cosine t minus 2 sine t cosine t. Well, I can do what I'm going to do next in any order that I choose, but I recognize these as a trig identity, right? This is minus sine of 2t, and this is also minus sine of 2t, which is minus 2 sine of 2t. And there's my derivative. I was actually fairly satisfied here, but I got to use some cool trig identities. Okay, well, let's see if I can really convince you that's true just by coming back to what f is and what x and y are. So, another way to think about this is through substitution. Plug x in for x and y in for y, and I create a function on the variable t. Cosine squared t minus sine squared t, that's a double angle formula for cosine. So here I have now really a function just on the variable t, f of t is equal to cosine of 2t. And so if I just take the derivative, I'll get df dt. Well, that's minus sine of 2t and then times 2 because of the chain rule from Calc 1. So whether I figure out the function itself on the variable t by substitution or I use the chain rule, I got the same thing. And that makes me very happy. So, there are situations where this will be more convenient, or we might just need to know the chain rule for other purposes. So I don't want you thinking that we can just plug stuff in and do this every time, but it is a nice way to check to make sure our chain rule works and makes sense. Now I want to talk about what this function is. If I think about these as parametric equations, I could even think of them as the components of a vector function, which would trace out the unit circle in the xy plane. Going that way. Okay, so I plug those xy's from the xy plane into the function and I get z's. So one way I could think about that is by thinking about the xy plane. In the domain I'd have a circle, and then when I find the z-coordinate, I have a path moving along this saddle. I have a path moving along this hyperbolic paraboloid. There's a link below this video in the description on YouTube and on our Moodle course page to a GeoGebra app that shows you the curve I'm talking about. And so what we've really done is found the derivative of f with respect to t of that path. And so what this really is the rate of change of z with respect to the parameter t.